All right, guys, so how are we doing?
Pretty good.
Good. Nice rainy day to be in here and working on some computer stuff.
Oh, yeah.
Okay, so Jake, did you get the email about, I
Yeah.
uploaded some videos yesterday?
Yep.
Okay, so we're good there, it sounds like. Okay, so I sent everybody an email yesterday, so I took the GoPro videos over the weekend, I put them on YouTube. There's links to them in Blackboard, so if you want to go back and review something, I'm going to try to put all those on there each day. So if we miss a class, then, or if you miss a class and we're talking about something you want to go back and review and see what we talked about, then they'll be there. Okay, that's the plan. It wasn't too bad getting it on there, so that worked okay, and I think the videos are reasonably watchable. It looked to me, watching them, that you could read the board and you could read what I was writing on the board and so forth. So hopefully that's useful. Now I've turned on usage statistics on those videos so that I can see, is anybody actually watching these things? Because, I mean, it was a couple hours for me to, you know, not me actually sitting there the whole time, but a couple hours to render the videos and then upload them to YouTube. So if I'm doing this and I'm seeing that absolutely nobody's even looking at these things, then it's kind of like, why am I spending this time to do this? Okay, so I would encourage you to utilize it if it's useful to you. I would assume that it's probably more useful for those people that are trying to take this class without being here on Tuesdays and Thursday mornings. So I'm mostly watching to see if they're watching them. Because this is a learning experience for me. I've got to learn, you know, I've not done a class where I haven't had butts in the classroom, so I've got to kind of learn what is the right way to reach out to those that are participating from work, kind of thing. Okay? So if you guys have any suggestions, I'll be happy to you know, address those, or you know, see if we can work something out. I mentioned something about using WebEx. Nobody's talked to me about that, and I haven't set that up yet. So that continues to be an option if anybody's interested, but we just need to set it up. Okay? All right, so we had a little bit of material that we went over on Thursday last week. We've got a little bit more material to look at today, and assignment 2 is up. I think I activated it yesterday. This is another reasonably short assignment, and the purpose of these is to show you what the computer is doing, to show you a little bit of what the math looks like that the computer is doing, and then assignment 3, then we'll actually get into actually using SolidWorks and so forth. Okay? I think assignment 3 is actually some SolidWorks assignments. I'll have to go back and review assignment 3. If not 3, then definitely assignment 4. So we've got a little bit of hand calculation to work on right now. Then we'll be getting into the SolidWorks stuff more. Jacob, I think you asked me about downloading in SolidWorks, and I think I forgot to respond to you. So we have some student licenses. I'm not sure what the exact procedure is for doing that. So we'll have to find that out. Maybe we do that after I talk for a little bit today. I'm pretty sure Rustin knows how to do it, so he might be the easiest way to find out what the process is. And if not him, then we'll talk to Greg Jones or whoever we need to talk to figure that out. Okay? Eric, you're nodding your head. Are you interested in the license too? Or?
Yeah, I mean, I'd like to be able to put it on my laptop so I can do it.
Yeah.
Okay. Well, we'll look for that after class today and see if we can work that out. Okay?
I have 2015 at work, but to use the FEA stuff, I have to have another key, which I think is like $10,000.
Okay. Yeah. Yeah. It's But they're not just going to spring that for you? Come on.
Same thing.
Pay your tuition and then $10,000 for software. I mean, come on.
It's just a text right off.
Yeah. Okay. So the PowerPoint that I want to look at today, we're going to look at how do we do a calculation with springs that is similar to what we're going to be doing later with the finite element software. I'm looking for 411. I can't read this at all.
Up a couple more. Right there.
Is that it? Yes, it was Josh too. Josh, you didn't sign it, did you? All right, so reviewing what we already talked about. So we talked about this on Thursday. The general procedure is define the geometry of the solid model. So that's doing the solid modeling in SolidWorks that you guys did in the CGT 110 and CGT 102 or whatever classes you had, CGT 163 or whatever we're calling it now. For our spring systems, we're not actually going to be using SolidWorks, so we can just define the geometry with a picture. We just have to know what is the arrangement of the springs that we're going to use to calculate our spring system. Okay? So you guys have done springs before, like in physics and statics. You know, we had a single spring that was stretched some given distance, and you guys are familiar with the equation F equals KX. Well, using the FEA procedure, we can take, instead of just doing one spring, we can do 2 springs or 4 springs or 1,000,000 springs or however many is necessary. We just have to know how they're all connected together. Okay? So we'll define the geometry, and in the case of the springs, we'll just have a picture of it. We have to define the constraints. We have to know where the springs are attached to something. Okay, we'll talk more about that when we actually look at a picture of a spring system. Right? We have to define where is displacements equal to 0, which is usually what our constraints are. There's other types of constraints. We apply the forces to the springs, whatever those might be, and then in the software we create a mesh, nodes and elements, and then we solve it. For our spring systems, we're going to create our stiffness matrix. And so I'll show you how to create a stiffness matrix. Normally the software does that for you, but since we're doing this by hand to start with, we will have to create a stiffness matrix. And then we'll use our matrix math that we went over on Thursday to then invert that matrix, multiply it by the forces, and then that'll give us our displacements of our spring system. Okay? And in the case of our evaluate the results, we're not going to have a graphical form because we're just doing calculations on paper. So valuing our results will be just, what is our displacements at each point. And then I'll also show you how to take your matrices and calculate what the forces are at the reaction point. Okay, so that's our task for today. It's really pretty simple, so I don't anticipate that it's going to take us a terribly long time to go over that. And then assignment 2 is just practice doing that. Okay? So, as we've talked about several times, you are familiar with this equation. Okay, so basic spring system. Rearranged it to be similar to the equation that we use, the KD equals F that we had in the previous slide, you should be familiar with that. The basic concept is when I put a force on a spring, it's going to deflect some distance x. And there is a linear relationship between the amount that it deflects and the force that is applied, and we call that our spring stiffness. That can be a matrix of values. If I have multiple springs in a system, then instead of having a single equation, I'm going to have a whole bunch of equations. And when I have lots and lots of equations that are linearly related, then I can write that as a matrix, and I can use matrix algebra to solve a huge system of equations all at once, which is where we take the inverse of the matrix and multiply it, and that gives us our solution. Okay? So that's what we're doing today. So this is big picture kind of stuff. So, as we talk about all of the different types of elements, I will show you things like this, and this is our elements definition. So when we take a structure and divide it up into the elements and the nodes, for the finite element process, how we divide up our structure depends on how we want to model the structure. So the simplest thing we can do is just assume that it's a bunch of little springs connected together. And then we can assume that those springs are capable of linear motion. So this spring has the possibility of displacement at this end. And the only possibility that we're talking about right now would be displacement in line with the axis of the spring. Okay, so this is similar like in statics we're talking about trusses. Trusses are only capable of tension and compression, right? So my basic element here is capable of displacement in the axial direction at node 1, or actually using this notation, node 0, and it's capable of displacement at node 1 in that same direction. This spring, by this definition, is not allowed to move perpendicular to the axis of the spring. Okay? That's a simplifying thing that I've created, keeping my equations really nice and simple. Then I'm limiting my springs to only stretching and compressing and nothing else. Okay? Now, obviously that's not a completely realistic scenario. In reality, I could have a spring that can move in all directions. And I can write the equations to do that, but they get much more complicated. We're trying to keep things really simple at this point. Okay? So my spring can move at both nodes in the axial direction only, and I can apply a force at either node in the axial direction only. No forces that are perpendicular to the spring. And as we go along, we're going to have similar slides to this, and we're going to get more and more and more complicated elements that are going to be more and more realistic to real-world problems. But I'm trying to not have you solve giant matrices by hand, and so we're keeping these simple at the beginning. Okay? So that's what my spring looks like. And so if I want to write a stiffness matrix for that spring, then my stiffness matrix looks like this. I take the value of the spring stiffness, I have positive values on the diagonal, and I have negative values in the other two locations. Okay? And so this times the displacements gives me the forces. So this is the Kx equals F that we looked at previously, just expressed in matrix form. Now, the thing that's a little bit different than what you've probably looked at in physics class, or I know that you've looked at in statics class, is we are saying that both ends of the spring can move. And so the amount of deflection on that spring would obviously be the difference between those two movements. So if the node 0 moved 1 inch and node 1 moved 2 inches, then obviously the deflection would be the difference between those, which would be 1 inch. Okay? But in this scenario, both ends of our spring can move, and we're going to let the math take care of that for us to calculate what the forces and deflections actually are. Okay? So, looking at the math, I said apply constraints here, but I can't apply constraints until I know what it actually looks like. Okay, so my assumption here with the applied constraints is that my spring actually looks like this, where node 0 is attached to a wall. Okay? So my constraint is node 0 is attached to the wall and it can't move. And if it can't move, then its displacements are 0. Okay? So that's what this means by applied constraints. So I'm kind of jumping ahead here. What I'm working towards is I want to solve this problem using the matrix approach that I just showed you. Okay? So if node 0 is attached to the wall, then my constraints is that x0 is equal to 0. So when I write out my equation, I put in a 0 here for x0 because it has no displacements at that node. Does that make sense to everybody? Okay? So for the rest of this, in this problem here, I've put now that k is equal to 50 and the force 50 pounds per inch and the force is equal to 10 pounds. Okay, so going back to this, my matrix now looks like, if I was to write this all out, my stiffness matrix is 50, negative 50, negative 50, 50. That's my stiffness matrix. My displacement matrix is 0 and x1. x1 is my unknown, is equal to, in my picture here, this F is equal to 10 pounds. We're putting it on node 1. So that would be the 10 pounds here, and I don't know what F0 is. Okay? So, right now, my stiffness matrix is this. In order to solve for x1, I need to invert this and multiply it by f. Remembering back from Thursday, how do I invert this matrix?
Find the determinant first.
Okay, I find the determinant first. What is the determinant of this matrix?
Zero.
Okay, it's this times this minus this times this, right? And what is that for this spring? It's 0, right? And if my determinant is 0, what does that mean?
You have no inverse. Or your inverse is 0, or it doesn't exist.
I have an invertible matrix, right? Okay, it's undefined. It's a mathematical impossibility because I have 1 over 0. Okay? And the reason I'm bringing this up right now is because just starting out with this really simple thing, if I don't apply any constraints, then my matrix is invertible. You know, if I left this as x0, my matrix is singular, it's invertible, it's not invertible, and thus I can't solve this problem. Okay? So this is what it looks like when you go in and you forget to put constraints in your model, and SolidWorks comes back and says, singular matrix, please apply some constraints. Because it's trying to invert this, and you can't invert this. So we have to apply some constraints. We have to put a 0 in here. And when I apply constraints, again, I'm a visual person. I like to visualize this as I don't need to worry about, this is position 1 in my displacements matrix. Okay? So I don't need to worry about row 1, and I don't need to worry about column 1. Okay? So by applying my constraints, I'm simplifying my math, and now I have a matrix that's 1 by 1 times a matrix that's 1 by 1 that equals a 1 by 1. And this matrix is invertible, right? not even really a matrix, right? But I can take 1 over 50, that's invertible, right? Okay? So this over here where I said, you know, over here, once I apply my constraints, draw a line through the row where my constraint is, draw a line through the column that corresponds to that constraint. And what's left is what we need to invert to do the math. Okay? Does that make sense? So 1 by 1 like this, then we're just left with 50 times x is equal to 10. This is the same f equals kx or kx equals f that we've done many times. And I'll show you how to do this with a 2 by 2 or a 3 by 3 in a second. Okay? So now to solve for x, I need to take the inverse of 50, which would be 1 over 50, multiply it by 10, and so what do I get for x? I get that x1 is equal to 1 over 50 times 10, so that would be 0.2, right? I did that math okay? 1/5 is 0.2, right? Okay? So in this problem right here, doing by this process with a single spring, this is how I would write my matrix. I apply my constraints. I do the math. That's the solve part. This is my answer. Okay? This is my displacements. This is what x1 is. Now, I can go back and find out what f0 is too. And we'll do that for the assignments as well. To do that, I need to go back to my original matrix and plug in what my displacement is. Okay, so x1 is equal to 0.2. So go back, I have 50, negative 50, I have negative 50, I have 50. Plug in my displacements, which are 0 and 0.2, equals. And I can solve for what f0 is. Just do matrix multiplication. So I have 50 times 0 plus negative 50 times 0.2. And negative 50 times 0.2 is going to give me back negative 10, right? So f0 is negative 10. And if I do the math here, I've got negative 50 times 0, which is 0, and then 50 times 0.2, and this is 10, and this gets me back to this number and this number had better stay the same, or we've got a problem. But what we're looking for is what is that number. And so my reaction there is, the math here is telling me that my reaction is equal to negative 10. Does that make sense? Damn right it does. One of you better have been in statics. If I got 10 pounds pulling that way, what do I have to have pulling the other way? 10 pounds. I didn't need to do the matrix to do that, to figure that out. You should use statics to figure that out. But if this was more complicated, what I'm trying to show you is have confidence that the math works and it'll give you the right number. It even gives us the right sign. It tells us it's negative. Okay? So this is really easy. How do I solve a spring system using matrix, the finite element method? We do the inverse, multiply by the forces to find the displacement, take the displacement, plug it back into the original equation, multiply it out, and find the forces. Okay? Questions about that? Okay. This one's kind of trivial because we've done these by hand without having to use matrix, but I wanted to show you that it works. Okay? So what happens if I have two springs? Well, the stiffness matrix gets bigger. Okay? And you have to construct the stiffness matrix depending on how the springs are connected together. All right, so look up there in the corner at my picture. I have node 0 on the wall. I have node 1 in the middle between the two springs, and I have node 2 that's at the end. Incidentally, you can label these nodes any way you want. We could go 2, 0, 1, or 1, 0, 2, or any permutation you want of that. The way you order it makes absolutely no sense. You just have to put the k's in the right spot in the matrix so that the math works out. So obviously it's going to be a little bit easier for us to visualize if we just do 0, 1, and 2. Okay? So I have my displacements at node 0, 1, and 2. And then this is my stiffness matrix. And look at this. The spring 1 is connected between node 0 and node 1. And so the K1s should go in the positions that correspond to the rows and columns of node 0 and 1. So 0, 1, 2, 0, 1, 2. Spring 1 is connected to 0 and 1. So we need a K, a negative K, a negative K, and a K, just like we did in the previous. Okay? Then when we look at spring 2, we have a little bit of overlap because spring 2 is also connected to node 1. And so that's why we have the plus K2 here, is because both K1 and K2 have to be on the node 1 position. And then the rest of it's filled out with a negative K, and positive K2. Okay? Anywhere, so I've got a 2 by 2 here, overlapping with a 2 by 2 here, where there's a little bit of overlap in that position right there, and that's why we're adding those two together. Does that make sense, how that's constructed? Is everybody okay with that?
So when you add another one to it, you're going to add another row. Another row, another column.
Yes, this would be another row and another column. And so if we had a third spring on the end, then how would this change? This position, this value here would be what? 0. This value would be, this value would be K3. This one would be negative K3, right. So you've seen the pattern? It's not real hard to do this the way this is, okay? Then over here we would have, the fourth column, we'd have 0, 0, negative K3, and then positive K3. Okay, so do you see how they overlap there? Okay? So this is what the entire matrix looks like for 2 springs. And I didn't do a whole example of this. This is what you're going to be doing for homework. Okay, so we're going to give you some values for K1 and K2, so you just plug in the values. If K1 is 10 and K2 is 20, then 10, negative 10, negative 10, 10 plus 20 would be 30, negative 20, negative 20, 20. And if I invert the matrix as shown, what am I going to find? Determinant's going to be 0, it's not invertible. So what I have to do, I have to apply constraints. Okay? So in that problem as shown up there, which one of the x values is 0? First one again, right? Node 0 is 0. So I put a 0 in here, draw my lines. Okay, so I don't need to worry about the top row. I don't need to worry about the first column. So the matrix that I'm going to invert is this 2 by 2 right here. Invert that, multiply it by the forces. I have to tell you what F1 and F2 is. And that will give us our displacements X1 and X2. Okay? You guys feel like that makes sense, or do you feel like you need to go through an example of what that looks like?
other places where we can check our work and stuff on Blackboard and stuff like that, so we make sure we got it, or?
I don't have an answer key on there, but,
We can probably look it up on Google or something, find it.
you know, or you can just show it to me and say, is this right? And I'll be
Okay.
happy to say, yeah, that's right. Okay? I didn't look at the assignment, so we're going on 1.5 years since I've looked at the assignment. I'm pretty sure that I asked, I don't know, somebody have Blackboard up, can you look real quick? Did I tell you you had to do any of them by hand, or what did I say on the assignment? Yeah, there we go, thank you. I should have brought a copy myself.
Says by hand there, so.
Okay, so properly write the stiffness matrix and the force equilibrium equation for the problem solving. It says solve by hand or using Excel the force equilibrium equation for the unknown forces and or displacements. Okay? So I did put by hand or using Excel. So you have to write the stiffness matrix. You have to then use either by calculating by hand or by using Excel, find the inverse of the 2x2 and then multiply it out. So obviously if you don't want to do all the hand calculations for inverting it, then use the damn Excel functions that I showed you, right? Okay, but you just have to set up a worksheet that will find the inverse for you and multiply it out. Okay, I don't mind letting Excel do the actual arithmetic for you because you have to know how to set it up in order to get it to work. Okay? That's why I'm letting you do it by Excel to do the inverse part. So we got problem number 1 and 2 is 2 springs, problem 3 and 4 is 2 springs, problem 5 and 6 are 3 springs. And the way I numbered these, like problem number 1 is find the displacements, problem number 2 is use those displacements to then find the reaction forces. So that's what we did over here. So on the homework, this would be like, this part would be problem 1 and this is problem 2 is the way those are numbered. Okay? Does that make sense? Everybody's okay with that? Okay. I think this is fairly easy, but I don't want to just assume that you think it's easy too. All right. And try it out, and of course, if you have troubles with it, then you let me know, and I'll be happy to work through it with you. Okay? I've been a little bit slow responding to some of your emails this week, but I'll try to do a little better job of responding a little bit quicker. So that's using springs, and then there's a couple problems for you to practice on how to actually do that. Okay? The other thing that I wanted to go over with you today is that we're first looking at this as springs that we're given the stiffness of those springs. But when we look at any structural element, you guys I think are familiar from materials and other classes that structures have the ability to elastically deform. And when they elastically deform, they're acting just like a spring like we use in physics class. Okay? So typically when I'm looking at a bar, I am given information like the length and the cross section, but I can use that information to come up with a spring stiffness just like the K that we get for traditional coil spring type situations. Okay? So this axial bar, if a force is applied to it, it will either stretch or compress just like a regular spring does. And I can figure out what that K rate is based on the properties of the axial bar. So if you remember from Strength of Materials, MET 211, we said for an axial bar that is straight with a constant cross section, the material is homogeneous and the load is directly axial, as long as we're below the proportional limit of the material, thinking about stress strain diagram, as long as we're not yielding, then the deformation of that bar is equal to FL over EA. You guys have seen that equation before, right? Okay, the deflection of that bar is equal to FL over EA. If we rewrite that, we take the FL over EA and just algebraically rearrange this. I'm moving the EA over here, dividing through by the L. I get EA over L times delta is equal to F. And the reason that I rearrange that is because then that looks like KX equals F, right? So the stiffness of the bar is EA over L, and I can use that just like we used to find the K rates of springs, and I can use that in a matrix if I'm using bars instead of springs. Okay, so right there we've just taken this up a notch, because I could then use this equation to calculate the deflection of a truss that is connected together, and I could use this finite element concept to figure out how it deforms and what loads are created in all the members for an entire truss now. Okay, so think about it in statics when we do the truss analysis. You do it by hand, and then I show you MD solids where you just define all the loads and the constraints and then click. What is MD solids doing? Something similar to this, okay? And that's how it does that so quickly, is because it is creating a stiffness matrix similar to this. I guess maybe MD solids is not the best example, because the MD solids tells you the forces, but it doesn't. You don't specify the size of all the members. So MD solids is not quite this complicated, because you don't have to actually define a cross section for each member. Okay, MD solids just assumes that they all have the same cross section, and then it spits out the forces that are in all the members. But using this process, using a similar type of math. Okay? So, on your assignment, your last problem is, instead of giving you the stiffness of springs, I gave you dimensions of bars. So you just need to figure out what the K is for the bars based on their size and materials, and then do the same thing exactly like you did for the previous problems. Okay? But we're working towards defining different types of elements, and we're going to use the concepts we've had in strength of materials to do that. So we're going to be looking at these equations like FL over EA and MC over I and those types of equations. We're going to start seeing those as we come up with these different types of definitions for elements. Okay? Think you can do that? Okay, so getting off the start here this semester, I've got relatively short topics for you, and I have some basic assignments that are hitting these points. So we have lecture today, a short assignment. On Blackboard, I had it made due next Tuesday, but honestly, again, you could probably get this done in an hour. So get it done as quickly as possible, then you've got your second assignment in. I think on the schedule, I think we're going to end up with a grand total of 10 assignments. Yeah. All right. So you get these two ones in the beginning. These are quick and easy, and you've already got 20% of your assignments done for the semester. We're going to have a lecture again on Thursday. So this week we're having lectures every day just to get us started and get some work going. Starting then next week on Tuesday, I'm not going to have a lecture planned until Thursday. Okay, so be watching that schedule. So, if you want to come in here on Tuesday to work, come in here to ask me questions, then certainly be here for that. But we have lecture this coming Thursday, and then for the schedule, then the following Thursday. So if you're taking off work, you could work and then do the work later if you want to, or however that works for you. Okay? So we'll be here again Thursday, and I'll have another short lecture for you. And we'll have assignment 3 will be, I'll talk about that with you on Thursday. Any questions or concerns? Okay. Have a good day, and I'll see you on Thursday.